Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. Today, I would like to conduct an asynchronous lecture on the inductive sensor and piezoelectric sensor. Okay, our slide is not that much, okay, but I hope that all of you can have a read, okay, and also can watch this asynchronous video for this course. Okay, the inductive sensors measures displacement by varying any three of the coil parameters. Okay, L equals to n square, okay, G and nu, okay, where n represents a number of turns of coil, G is the geometric form factor, and nu is the effective permeability of the medium. Okay, and each of the parameters can be changed by mechanical means. In an inductive sensors, okay, it is usually consists of these three elements, okay, these three components, which are the single coil, a reactive Wheatstone bridge, and then the linear voltage differential transformer. The advantage of the inductive sensor is that it is not affected by dielectric of this environment. Okay, means that it is not going to be affected by like dirt, okay, or it is not really it doesn't work with the physical contact. So it is very robust sensor. That's why one of the most popular application is that it is used to sense the inductance of uh, of uh, car. Okay, is because it can sense the changes in the inductance. It is usually used like at the intersection of the roads. Okay, so that's why if you look at the traffic light, okay, that we have, and it is like if you can see that it is not a time based. Okay, usually it is based on the inductive sensor. Okay, because it can detect the change in the inductance when a vehicle passes over or stops at the point. Okay, so this can be used to detect vehicles and adjust the timing of traffic signals. Okay, and it can provide alternating signals at the busy intersection. Okay, when needed. So this is the good thing. Okay, good thing about the inductive sensors. But one thing that is not good with inductive sensor, because it is made it is made from magnets. Okay, so it can be affected by external magnetic fields. Okay, so okay, just now I related uh, with the with the common application that we can see every day. Okay, how about for biomedical application? Okay, so the reactive Wheatstone bridge sensor, okay, together with the inductive sensor, okay, is used for measurement of arterial and venous blood pressure. So it is similar to what we have for the traffic light. Okay, I can sense the different of the displacement of our blood pressure. Okay, because if you still remember how does the blood pressure being measured? Okay, about how the blood, okay, is will stream. Okay, once you have already what we call let go the pressure, okay, until you can hear the cough for sound. Okay, so inductive sensor is very good. Okay, it's very good to detect the arterial and venous blood pressure. Okay, because and then the transduction occurs because of a change of position of the inductor score. Okay, but okay, this is only position data. Okay, because it's all okay about position. Okay, unless the applied force occurs against some other force such as spring. Okay, let's go to the other slides. Okay, okay. The amplitude is proportional to the magnitude of the applied pressure. Okay, this is how we get the reading of the blood pressure. Okay, this is just to give you some imagination how it's going to how is reading. Okay, how we got the reading. Okay, the amplitude is proportional to the magnitude of the blood pressure, while the phase indicates whether the pressure is positive. Okay, means that it is in compression, or negative, whether it's in vacuum. Okay, okay, and then we have this LVDT. Okay, LVDT stands for linear variable differential transformer. Okay, linear voltage differential transformer composed of a primary coil and two secondary coils in the series. Okay, I hope you can find uh, the diagram of it. Okay, the diagram of it. Okay, coupling is achieved by motion of high permeability alloy core between them. Okay, the secondary coils are connected in position. Okay, to increase the region of linearity. So that's why we have this formation. Okay, you have the primary coil and then the secondary coils. Okay, because we want to increase the region of linearity. Okay, the primary coil is sinusoidally excited, and the frequency used is between the 60 hertz to 20 kilohertz. So there's a big range of it, 60 hertz, okay, and then 20 kilohertz. Okay. Alternating magnetic field induces nearly equal voltages in both the secondary coils. Okay, so how about the output voltage? Okay, so the output voltage, okay, is given by V1 minus V2. Okay, so this when you see the equation, that's why you can appreciate why we have there's first secondary coil and then the secondary coil. We have the primary coil and then you have the secondary coil. So okay, so we will know how much of the voltage out. Okay, how much of the voltage out from here. Okay, by the voltage induced in the the voltage induced in the first secondary coil minus the V2. Okay, so when a core is symmetrical placed, okay, the two secondary voltages are equal, and the output signal is zero. So this is how this is done. Okay. Okay. So what are the characteristics of LVDT? Okay. Okay. It has a linearity over a large range. Okay. Because if you do a measurement, okay, you need to have a high linearity. Okay, you need to have a high linearity so that you can measure a lot of things. Okay, um, uh, you can you can expect. Okay, you can expect many things. Okay, if it's linear. If it is non-linear, so it's a trouble for you to measure many things. Okay, okay. So the phase change of 180 degrees. Okay, when core passes enter position, and then it has saturation on the end. Okay, okay. Advantage. So if that's why we have to know a reason, like I told you in the beginning of the lecture. Okay, in the beginning of the lecture, um, the why we have a lot of these sensors. Okay, capacitive, strength gauge, okay, and so on. So why we or why there's a lot of differences? Okay, because of because of the applications, and also maybe the advantage. Okay, maybe certain applications need more sensitive readings, okay, more sensitive readings, okay. So for this application, LVDT is better than strain gauges, maybe, but sometimes maybe you don't really need uh, a sensitive sensor, and maybe from there you can get a cheaper sensor. So maybe this provide an option for you. Okay, this provide an option for you. So maybe you can use strain gauge, which is a which is cheaper than LVDT. So these are the things that you have to consider as an engineer. Okay, you have to consider as an engineer about the cost. Okay, about what you are going to measure. For instance, that's why sometimes, okay, this is for like for those who use who have used I think you have gone to the biomaterial lab. Okay, for instance, the the weighing machine, the weighing equipment, you can see that, okay, some of them can, it is just to weigh things, okay. It can be up to 3,000 to 4,000, because it is able to measure up to like 4 decimal points, okay. Whereas you can get maybe a measuring scale that is 20 ringgit in the market. So um, this is the reason, okay, why you need to consider all the sensors. Okay, you need to consider all these kind of sensors, because you want to see, okay, what type of application you want, okay, how sensitive it can be, okay, how costly, okay, maybe because some people they really need to be very accurate, okay. So you have, maybe you can, yeah, that's why some equipment is much more expensive than the others, because they will look into the market. Okay, that's why sometimes, okay, that's why, okay, you can see that with weighing machine, okay, weighing equipment, okay, for the 4 decimal points, you can up to 3,000 to 4,000 ringgit, okay. But then for our weighing scale, okay, weighing scale for us to use, okay, maybe it is just not more than 30 ringgit, with 30 ringgit, okay. So because, and then another thing that you have to consider is about, okay, who are going to use it. Not many people are going to use the weighing equipment, okay, that is sensitive up to 4 decimal points, okay. But okay, a lot of people, okay, want to measure their own weight. So that's why you have more market. You have more market. That's why it can be so. Uh, it can be so cheap, and not so cheap lah. I mean, it's cheap. Okay, it's cheaper. Okay, one equipment is expensive, but the function is the same. Okay, you just want to measure weight. Okay. Okay. However, okay, there's disadvantage. There's a disadvantage for inductive sensor. Okay. In my questions for many of the courses, okay, many of the courses, I love to ask about the advantages, disadvantages. So um, you have to know, because that's why you have to relate with the cost outcome. You have to relate with the cost outcome. Okay, what are the advantages and also disadvantages of the sensors that we're going to use? Okay, so when I just talk about the price, okay, this is one of the thing. Okay, if the equipment, okay, just use strain gauge, maybe it is not that expensive. Reason why, you can see the reason. Okay, because this LVDT, this LVDT, okay, requires more complex signal processing instrumentation. Okay, so this is when you have the extra thing, okay, to add on, okay, for instance, to process the signals, okay, maybe, okay. So this is the reason why it becomes more expensive, okay, and then it needs a phase sensitive demodulator, okay, to determine the direction of displacement. So these are the things that maybe you have a more accurate result, okay, you have a better result in some way, okay, it is more sensitive, you have better accuracy, okay, better accuracy, of course, with a better repeatable results, okay, But the problem is that, okay, you have uh, you have more complex, okay, more complex signal processing procedure you have to use, okay, and maybe you have a uh, uh, you got to have other additional components, okay, to help to assist in terms of measurement, okay. So you can see, okay, you can see from the lecture notes, okay, you can see the ability, okay, in for to measure pressure, okay, displacement and force. Okay, then we have another type of sensor, okay. We have another type of sensors which are which is the piezoelectric sensors. Okay, we have piezoelectric sensors everywhere actually, okay. The easiest way for me to uh, like to like to make you imagine is about the probe that's being used for ultrasound. Okay, okay. So this is one good sensor. Okay, okay. When you know the property of a material, okay, um, the physics of it. Okay, so you know how does it work. Okay, one thing about piezoelectric material is that when it is mechanically strained, okay, it will generate electrical potential. So this is the advantage of this is one of the characteristic of the piezoelectric materials. Okay, so this electrical potential, okay, causes physical deformation of the material. So this is about, okay, so it's about the material become deformed, okay, it changes the shape, okay. So uh, when there's deformation of shape, okay, you can actually measure physiological displacement. So that's why I relate it with the ultrasound, okay, when you want to when you want to scan fetus, okay, there's a displacement, the movement of the babies, okay, the movement of the fetus, okay. Uh, so this is good, okay, this is good, okay. So you can use the okay physiological materials, okay, so you can see how does it react with the movement, okay. I hope you can find other application of a piezoelectric sensor, okay. So there's a lot actually uh, the application, okay, but do find it, okay, from your readings, okay. Please do some searching in Wikipedia, okay, uh, because the piezoelectric sensor is not only used here, okay, in this course, okay, but you may use it even like in my course in the future, like for instance, biosensor and biomass. Okay, so how does it work? Okay, the principle of operation. Okay, when an asymmetrical okay, crystal lattice. Okay, so now you go to the lattice of the crystal material. Okay, when this distorted, okay, a charge reorientation takes place, causing a relative displacement of negative positive charges. Okay, so you can see that there's a what you call there's a physical. Okay, there's a mechanically things happening, okay, but it resulted in uh, in in the charges, okay, in the charges of the of the material, okay. The displaced internal charges induce surface charges of opposite polarity on opposite sides of the crystal, okay. And then okay, how you can you appreciate what happened here is that, okay, there's actually, okay, these surface charges, you can measure the voltage difference between the electrodes, okay. So the surface charge determined by measuring voltage difference between electrodes. So this is diagram, okay, diagram what happening there, okay. So okay, you have the uh, the polarized molecule and so on, okay. Okay. Initially, we assume infinite leakage resistance. Okay, the total induced charge is directly proportional to the applied force. F with K as the piezoelectric constants. Okay, so you have the charge Q. Okay, then you have K. Okay, as the piezoelectric constant. Okay, and then you have the applied force. So the voltage change assumes the system acts like a parallel plate capacitor. So this is one of the assumption. Okay, this is one of the assumption. Okay. Okay. Typical values for K are 2.3, okay, P, C, N, okay, for quartz and 140 PC, okay, per N for barium titanium. So these are the two materials, okay, that is that have a piezoelectric characteristics, okay, for a sensor of 1 centimeter square area and 1 millimeter thickness with an applied force due to 10 gram weight. The output voltage for quartz and barium titanite is 0.23 millivolts and 40 millivolts respectively. So you can see that the output, okay, is different, okay, for quartz and for barium titanite. Okay, so okay, maybe if you want more voltage, okay, maybe you can and then your it's maybe easier for you to detect. Okay, maybe you can use barium titanate, but you have to. But one thing, okay, it's about cost again. Cost again. Okay, maybe most probably barium titanate is more expensive compared to quartz. Okay. Okay, we come to the end of the lecture today. Okay, so you can see, okay, these are the various modes of operation of our piezoelectric sensors, okay, depending on the material, the crystallographic orientation of the plate, okay. So you have to see, okay, from the thickness or longitudinal compression, okay, transversal compression, thickness shear action, and phase shear action. So I hope that, okay, you can have a extra reading on this, all these types of sensors, okay. Um, I hope, okay, you guys have some basic idea on the inductive and also piezoelectric sensors, okay, and do find more, okay, through the maybe your YouTube channel, okay, you can find some videos on this piezoelectric sensors, inductive sensors, also other type of sensors that I've given the lecture last Friday. Okay, thank you very much for your attention. Okay, I hope that okay, you guys can play, okay, this recording over and over again. Okay, and please, okay, remember the basic principles. Okay, the advantage and the disadvantages. Okay, and then also the important equation for how the sensors work. Okay, thank you very much. Okay, see you in another lecture. Thank you very much. Assalamualaikum.